Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to start with a new chapter, which is chapter number 4. In chapter number 4, we will learn chi-square test. Basically, this chapter is about chi-square test. Chi-square test is basically for a categorical data only. So the objective of this chapter is to explain the rationale of goodness of fit test, and then we're going to explain the rationale for test of for independence. So we're going to learn two tests basically in this chapter: goodness of fit test and test for independent. Right. So the logic behind goodness of fit test is when in previous chapter we have assumed that a distribution is appropriate for the given data given, right? But we then can focus on the estimating and testing hypothesis about the parameter from this distribution. However, the question is, does the data support assumption that the particular type of distribution is appropriate? So we want to know whether the type of distribution yang kita guna dalam hypothesis tu, right, is it appropriate for that statistical test or not? So that's why we're going to derive or test goodness of fit test, right? So now look at this example, right? Suppose we roll an apparently a normal 6-sided die 60 times, right? And we obtain the following observation frequency. So when we got number 1 ada 4 kali, right? Number 2 7 times, number 6 17 times. But if you can see from this result, number 3 is 60 times and number 6 17 times. So this is the most possible frequent outcome for rolling 60 times die, right? So the question is, we want to know whether this die is fair or biased, right? So with a fair die, the probability of each outcome is 1/6. We already learned this on QMT 161, right? So a probability for each die, right? So let's say I have X, and this is a probability of X. 1, 2, 3, 4, 5, and 6. So each probability for getting number in die is 1/6. So this is fair dice. If you have a fair dice, so the probability of each outcome is 1/6, right? So with 60 toes, right, the expected frequency is 60 multiplied with 1/6. So the formula for expected frequency is n multiplied with probability of each outcome, right? So n multiplied with p, right? This is the formula for expected frequency. This is the most important part. So if from the outcome we can calculate the expected frequency. So number of trial multiplied with the probability for each outcome. So it became 60 multiplied with 1/6. It should be equal to 10. So each outcome should have 10 expected frequency. That's why we got this one lah, right? So from the expected frequency, we can calculate the difference between observed frequency and the expected frequency. The observed frequency minus expected frequency means 4 minus 10 equal to -6. So we will use the difference between observed and expected frequency to calculate the test statistic, which is a chi-squared distribution, right? So the question is, we want to know whether the die is fair or biased, right? So now, since you already calculate the difference between observed and expected frequency, if you can see if we this is when we toast 60 times, right? If we toast 660 times, we will obtain the biggest number lah. But again, if you can see, the expected frequency will remain the same, right? So 660 multiply with 1/6, so you will get 110, right? Okay, so this time observed and expected frequency seems remarkably close. So kita akan nampak dia makin lama makin dekat. So simply we can say that this die is a fair die, right? Kalau kita nampak daripada sini, kita boleh kata dia adalah fair die lah. Sebab dia lebih banyak trial yang kita buat, dia menghampiri expected frequency, right? So now, to understand this further, right? So we understand the expected frequency and the difference between observed and expected frequency. Now, when we combine the idea of both different and relative size, right, we can get observed minus expected divided by observed minus expected multiply. This is multiply divided by expected. So this is the goodness of fit for outcome for 660 trial. So this formula will constantly apply for any trial, for any experiment that follow binomial distribution, right? So the smaller this quantity, if you get this value is small, you get the value this value is small value, so the distribution will better fit, right? So any significantly large value of chi-squared will suggest a lack of fit. So this is the based on our simulation lah. If you can try to prove this one by trying to do a simulation on this experiment. So the aggregation for each outcome, so right, so this one is a goodness of fit. Fit is observation minus expected square divided by expected value of each outcome. So this one, each outcome ada dia punya goodness of fit, right? So the total or summation of all goodness of fit, right? The total of all goodness of fit is a chi-square distribution, right? Is a chi-square distribution. So this is just a knowledge, right? Just information for you to understand. So where m is the number of different outcome. So for this case, we have 6 dice, 6 our possible outcome. So m should be equal to 6 lah. So the different sample given will give different set of observed frequency and hence different value of chi-square distribution lah, right? So this chi-square distribution is only applicable for categorical data, right? So now analysis for categorical data. Many experiment result in measurement are qualitative or categorical rather than qualitative, right? So for example, in a medical study, we only use qualitative data, which is a categorical data, whether you alive or die, whether you sihat ataupun tak sihat, right? So this is another example. People classified by ethnic origin, car classified by color. So this is one of the example of categorical data lah. So when we have a categorical data, right, normally we should expect more than one categorical level, right? So in multinomial experiment, right, it consists of n identical trial. So this is related to binomial distribution. It's closely related to binomial distribution, where in binomial distribution we have 2 possible outcome and trial fixed number of probability, right? Probability of success, it should be fixed. right? In multinomial, same, right? Binomial and multinomial. So in multinomial, we have n identical trial with repetition, right? Each trial result in one of k possible outcome, or means it's categorical data lah, right? Means you should have more than or equal to 2 outcome, right? Whether live or die, right? So the third condition is the probability that the outcome fall into a particular category on a single trial is probability of I and remain constant from trial to trial. If you can see, condition 1, 2 and 3 follow binomial, same as binomial distribution. And number 4 also same. Each trial are independent. So we are interested in a number of outcome in each category. So means we are interested on observed value, observed frequency, right? So with the summation of observed is equal to number of trial, right? So this is just a review on the binomial distribution. We try to combine it to a new dimension, which is multinomial experiment, right? So basically all the condition for multinomial experiment are same as binomial experiment, right? The difference only lies on condition number 2, where the level of each category is more than 2, right? In binomial distribution, we should only have 2 category level, right? Level of category. For multinomial, we should have more than 2 level of category lah. But if you have only 2, also can use multinomial experiment, right? But for the term to be changed to multinomial experiment, the k result, the possible outcome should be more than 2. Right. So now we move to the goodness of fit test, right? So this is the simplest of the application. A single categorical variable is measured, right? And exact numerical value are specified for each probability, right? The probability can be measured by the observed frequency, can remember the basic theory of probability. Right, the frequency obtained from the performance of experiment are called observed frequency, right? So if you can see this result, right? So the possible outcome, right? The observed frequency is the number of how many you roll a die, right? So the total here should be 60 lah kat sini, right? Dia takkan berubah. So the total should be 60, right? It should be remain 60. Right now, and then the expected frequency denote as E, right? The expected frequency denote as E are the frequency that we expect to obtain if the null hypothesis is true, right? What is our null hypothesis for goodness of fit? Null hypothesis, probability of 1 is equal to some value. This is some value, probability not P naught. Alternative hypothesis, probability 1 is not equal to some value, right? This is some value lah. Some value ada tak P naught, right? So this is the hypothesis for goodness of fit, right? So the expected frequency of a category can be calculated by n multiplied with P, where n is the sample size and P is the probability of success, right? Probability of success, probability that we are interested to study, right? Now, in chi-squared distribution, right? Goodness of fit, of course, we're going to use a chi-squared distribution, right? A chi-squared distribution should have a degree of freedom. If you still remember, the chi-squared distribution also based on binomial distribution, right? So it's skewed to the right distribution, right? This is, let's say, this is a rejection region, and this is acceptance region, and this is a chi-squared. This is a chi-squared 1 minus alpha. For example, this is alpha lah. Let's say chi-squared alpha 0.05. Alpha 0.05. And then we should have a degree of freedom here, right? So that's why, if you still remember, in a chi-square distribution, we have a degree of freedom. For degree of freedom for chi-square distribution, our goodness of fit test is k minus 1. Means that, what is the k? K is the number of possible outcome. Let's say you are rolling a die. Rolling a die, possible outcome, you have 1, 2, 3, 4, 5, and 6, right? So this is, let's say, sample space for rolling a die. So k should be equal to 6 category, right? Let's say you have possible outcome for tossing a coin, right? Tossing a coin, you have head or tail. So k should be equal to 2. But in our case here, we are measuring for multinomial experiment, right? But multinomial experiment also came from binomial distribution, binomial experiment. So either one can be used to our test, right? Right. So hopefully you understand this one, right? So test statistic for goodness of fit test, right, is a chi-square distribution. So chi-square distribution is a Pearson chi-square statistic calculated. This is a formula. We are taking a summation for each goodness of fit, right? Remember, goodness of fit value can be calculated by using observed minus expected. Means this is observed for 1, expected 1, minus expected, then you square, divide by expected value. So the summation of all goodness of fit value ni we call as a chi-square distribution, right? Pearson chi-square statistics. And remember that Pearson chi-square goodness of fit test is always right tail. Macam tadi I draw lah, it's a right sided test, right? So some note before we go for the example number 1, right? The test statistic chi-squared has only approximate a chi-square distribution, right? So in a chi-square distribution, if the expected is actually Pearson chi-square distribution, this formula is only recommended when each outcome, the expected value for each outcome is more than or equal to 5, right? So means that when you look at this table again, the expected frequency here, it should be for each category, for each outcome, it should be more than or equal to 5. Right? If you have less than 5, you cannot use this formula, right? You cannot use this formula, right? If you have the expected frequency for each outcome more than or equal to 5, then baru you boleh pakai this formula lah, right? So the hypothesis statement for goodness of fit tests are different so from a previous chapter, right? The null hypothesis model is correct as specified when whether it follows a binomial distribution, whether it follows a Poisson distribution, right? The alternative hypothesis, the model is not correct. So when we are calculating the p-value, right, we are hoping to accept null hypothesis, right? So then we can proceed with that distribution to conclude our analysis, right? Now look at example number 1. In this example, a bank has an ATM installed inside the bank, and it is available to its customer only from 7 a.m. to 6 p.m. Monday to Friday. So we have 5 days operation of ATM lah, 5 days, right? So the manager of the bank wanted to investigate if the percentage of the transaction made on this ATM is same for each 5 days, right? Adakah dia punya transaction tu sama tak from Monday to Friday of the week? She randomly select one week, right, and count the number of transaction made from this ATM machine for each 5 day for this 5 days during the week. The information she obtained is given a following table, right? We have a table, right, where the number of user representing the number of transaction and for these days, right? So we are refer transaction as people or user lah. So how many user are using this ATM machine, right? So now this is the frequency table, right? We know that this is the observed frequency, right? So now if you want to calculate the expected frequency, right, the expected frequency, say expected frequency, the formula for expected frequency is, if you can look at my previous slide, the expected frequency is n multiplied with p, where n is the number of observed frequency multiplied with the probability for each days, right? So we have 5 days, right? So this is, let's say I create a new table for a probability table. So I have x, which is represent days. This is a probability of x. So Monday, Tuesday, Wednesday, Thursday, and Friday. So let's assume all days are equal. So we want to know whether the hypothesis here is, what is our hypothesis? Based on the manager investigation objective, she want to investigate if the percentage of transaction made from ATM is same for each of the 5 days. So the null hypothesis, P1 is equal to P2, P3, P4 equal to P5. Alternative hypothesis, at least one day is not same, right? At least sekurang-kurang satu hari tak sama. So we're going to reject the claim, right? So if you want to make this if our assumption is all the transactions are same, it should be 5 days divided by 5, so 1 over 5. So each day has same probability. The total should be equal to 1, right? So this is the probability that we assume lah, right? So the probability should be equal to 1 over 5 lah, so which is 0.2, right? So we want to test at 1% significant, 1% level of significance, right? We want to test at 1% level of significance. Can we reject null hypothesis that the proportion of people who use this ATM machine for these 5 days is same, right? So we want to reject null hypothesis. We want to conclude that at least one day is not same. So assume that this week is a typical of all weeks regard to the use of ATM machine. So now our solution here is, we first state the null hypothesis and alternative hypothesis, right? The null hypothesis is all the probability of using ATM machine are equal, which is 0.2, 1 over 5 lah. So it's also equal to 1 over 5. At least 1 of 5 proportion are not equal to 0.2. So we know from the statement we have 5 category. 5 category means we have 5 days, right? 5 days which ATM is used. This is a multinomial experiment lah. If you only have 2 category, that is going to be a binomial distribution. So we're going to use a chi-square distribution to make this test. So this is going to be a right tail test lah. So if you look at the distribution curve, it should be a right tail test. The rejection area is 0.01. This is our alpha. This is our rejection region. This is acceptance region. So our K is equal to 5. So our degree of freedom should be equal to K minus 1, which is equal to 4. Right? So the critical value of a chi-squared is going to be a chi-squared with 0.01 degree of freedom, and the 0.01 is our level of significance, and 4 degree of freedom. So this one going to be 13.277. Right. Okay. So this is the graph, the distribution curve for a binomial distribution. Right. So now, from that, we need to create one table to calculate the chi-squared value. Remember our chi-squared value, the chi-squared value somewhere here or here, right? So chi-squared is observed frequency minus expected frequency squared divided by expected frequency, right? So this is a goodness of fit. We need to take the total of goodness of fit for each category. So I equal to 1 until 5. So this is the test of chi-squared test. So now we create a new table consists of observed frequency and the probability of success. Probability of success means probability of using the ATM machine lah, right? So we got 1/5. Remember tadi kita dah buat 1/5 for each days, because our claim is all days have a same transaction. And then we create another column which is expected frequency. Expected frequency is n multiplied with p, which is the total n, the total value of observed frequency. This is the total. You can apply 1200. Total multiplied with 0.2, which is 240. So this is 240 for each category, right? So then we going to take a difference of observed frequency minus expected value. So 253 minus 240, you got 13. 197 minus 240, you got negative 43. So this is the the difference of observed frequency and expected frequency. And then the next column, we will take a square value. If you don't want to take a square, just masuk dalam formula pun also can, no worries, right? So I just do step by step. So 13 square, you dapat 169. 43 square, 1849, right? So the next column is we are calculating goodness of fit value, right? Goodness of fit value, observed value minus expected square, which is this one, right? Divide by the expected frequency, which is this one, right? So 169 divided by 240, you will get 0.704, right? So before we proceed with the chi-squared value, before we proceed with this one, step number 1, 2, 3, 4, step number 4, 5, and 6, we need to check, right? We need to check the expected frequency for each cell should more than or equal to 5. Remember this one? I already told you the approximation to be accurate, the statistician recommend expected frequency more than or equal to 5 for each cell, right? If we have the expected value less than 5, we need to combine. Either we combine or we omit that category. Normally we combine the category, right? So now I will show you in the next example when we have the expected value less than 5, right? what we need to do. So now we already calculate the goodness of fit test, the goodness of fit value. We need to sum all the value. You will get 23.18. So 23.18 is our Pearson chi-squared statistic. This is our test statistics, right? 23.18. So now comparing 23.18 with the critical region. So 23.18 should be over here lah, 23.18. So it lies on the rejection region, right? When it lies on the rejection region, so our decision is to reject null hypothesis if chi-squared calculated is more than chi-squared value, right? Since the chi-squared calculated is 23.18 is larger than critical value, then it fall under rejection region. So then we can reject null hypothesis. So our conclusion here is we can reject null hypothesis that the proportion of people who use this ATM each of 5 days is same. So we have a sufficient evidence to indicate that at least one of the 5 days are not same. Is having either high transaction or low transaction. So to determine whether it has a high transaction or low transaction, we can use frequency, observed frequency lah. You can see observed frequency. You can look at on Tuesday, right? Tuesday it has a low transaction compared to others days lah. Monday, Wednesday, Thursday and Friday, right? So that's why we reject null hypothesis. This is our argument, right? Our test to solve the problem. Now, basically, do you understand the concept of calculating goodness of fit test? Can you comment? Hello, can you comment please? Do you understand? Please comment on chat box. Either you understand or not understand. A little. Yes sir. Right. So to enhance your understanding, right, try to copy this example, right, example number 2, right. We try to do it together, right. I'm giving you 3 minutes to copy this example lah, example number 2, and we try to do it together, right. Now we shall continue now. So now example number 2, a city expressway with 4 lanes in each direction was studied to, we have 4 lanes in each direction to see whether driver preferred to drive on inside lanes, right? So a total of 1,000 automobiles were observed during the heavy early morning traffic and their respective lane recorded, right? So we want to know which lane drivers are preferred, right? So the results are shown as below. So lane number 1 we have 294, lane number 2 276, lane number 3 238, number 4 192, right? The total should be equal to 1,000 lah. The total 1,000, right? So the question is, do the data present sufficient evidence to indicate some lanes are preferred over the others? We need to test the hypothesis at alpha 0.05. So now our hypothesis is null hypothesis, probability of using the first lane are same as second lane, third lane and fourth lane. So the probability for each lane should be 1/4, 1/4, 1/4, 1/4. Right, so this is our claim, 1/4. Alternative hypothesis, at least one lane, which is one probability, is not equal. So maybe drivers are preferred lane number 3, lane number 4, or lane number 1. So our alpha is 0.05. So now we're going to test statistic. So since we have 4 lanes, so we have k equal to 4. So this is a multinomial experiment. This is a multinomial experiment, right? So next step is we need to create a table, right? Since we're going to calculate the goodness of fit value and the chi-squared value. So this is a lanes, right? So we have lane number 1, lane number 2, number 3, and number 4, right? So we have observed frequency, so this is a zero observed frequency. This is 294, 274, 238, and this is 192. And then we need to calculate the expected frequency, which is E, right? The expected frequency is calculated by using N multiplied with P. PI. PI means probability of for each category lah. So N is the total of frequency. The total of frequency is 1000, right? So N equal to 1000, P equal to 1 over 4. So this is 1 over 4. So the total multiplication of these two is 250. So each category having same expected frequency, because our argument is all lane having same preference, 250, 250. And then the next column is we're going to calculate the difference between observed and expected, right? Observed and expected, 294 minus 250 should be equal to 44. This is 26, negative 12, negative 58, right? And then we're going to calculate the square of the difference of observed and expected. So this one, 44 squared should be 1936. This is 676, 144, and this is 3364. And next we're going to calculate the goodness of fit value. Goodness of fit value is observed minus expected square divided by expected, right? So this is the same value here, 1936 divided by the expected frequency, right? So this one should be 7.744, 2.704, 0.576, and the last one is 13.456, right? Now, before we conclude whether we can use this value, right, we need to look at the expected frequency. All the expected frequency is more than or equal to 5. It's more than 5, 250, right? So obviously you can use Pearson chi-square. This is the total of the expected goodness of fit, which is 24.48, right? So our chi-squared calculated is equal to 24.48. Now, since we already calculate the chi-squared value, now we can create a critical region. we know from the previous from the statement we have 4 category. This is a multinomial experiment. So multinomial experiment is same as a chi-square distribution, right? So you should have a right tail distribution, right? So let's say this is 0.05 our alpha, right? This is our rejection region lah. This is a rejection region. This is acceptance region. So our chi-squared here should be 0.05 with the degree of freedom. Our k is equal to 4. Degree of freedom is equal to k minus 1, equal to 4 minus 1. Oops. So 4 minus 1 equal to 3 lah. So this is going to be 3. So with this one should be equal to 7.81473 by looking at the statistical table. Right. So our decision is we're going to reject null hypothesis if chi-squared calculated is more than chi-squared 0.05 with 3 degree of freedom. So since chi-squared calculated is 24.4, which is somewhere here, is more than chi-squared with 3 degree of freedom, so we reject HO. Right? So our conclusion, so the data present sufficient evidence to indicate that some lanes are preferred over others. Right? So we reject null hypothesis. We can say that at least one lane are not equal. So one lane are preferred over others. Right? So if you look at the value of frequency table here, you can see lane number 4 is the least drivers use that lane, right? So means that lane number 1, 2 and 3 are preferred by the drivers compared to lane number 4. So that's how we do a statistical test. Right. So far, ada soalan tak? Soalan? Any questions so far? Please comment on chat box. The method is same for this part lah, right? We will see the different part on the next topic, right? I just giving you the same example, right? Now, so for example number 3 and number 4 is a same procedure, right? So before we go for others application, right? So we're going to stop here first. So example number 3 and example number 4, please treat this one as your homework. Please do it by yourself, right? If you don't understand, please discuss with your friends, and please ask me if you stuck at to solve the problem. Basically, example number 3 are same as the procedure to answer example number 3 and example number 4 are same as example number 1 and number 2, right? So roughly let's go through roughly. I tak nak buat pun, I just tunjuk dekat you. So the proportion of blood type A, B and O, A, B and AB, we have 4 blood types, right? K equal to 4. Of a particular country are known to be on the ratio 50, 30, 15 and 5. So now this is a bit different because the probability for each blood type are different. So this is going to be 1 over 2. This is going to be 2 over 10. Sorry, 3 over 10. 30%, right? And this is going to be 3 over 20. And the last one is 1 over 20. So better you do a calculation again, right? So the total should be 100, right? So now, of course, the value of expected frequency should be different lah, right? Dia tak sama, right? So basically the procedure are same, right? So the difference here is when the value of probability is not equal, right? So this is a research team, right? Bukan research team investigate a small isolated community on the country and obtain the following blood types lah. So how many this is observed frequency, right? This is OI, and then you need to calculate the expected frequency, which is N multiplied with P. So the P here is 1 over 2. This is 3 over 10. This is 1 over this is 3 over 20. This is 1 over 2. And of course, this one, the total here should be equal to 170. So 170 multiplied with 1 over 2 is 85. This is 51. This is 25.5. This is 8.5. So by looking at this one, semua more than 5. So you can proceed, right? So the steps are same, right? So hope you understand how to solve example number 3. And example number 4 are same as example number 3. Right? In past 2 years, XYZ supermarket has observed the following distribution modes of payment expressed in cash 41%, check is 24%, credit card is 26%, and others is 9%. So now we have 4, K equal to 4, right? Cash, check, credit card, others, right? And of course, the probability of success is not equal, right? Probability of success for cash is 0.41. This is 0.24, 0.26, and 0.09. And now we can find the expected frequency. The total here should be equal to 495. You multiply lah. 495 multiply with 0.41 is become 202.95 and so on lah. Right, tak sama lah. 118.8. And then you can calculate the goodness of fit value by looking at the expected frequency more than or equal to 5. Right? Is there any question so far? Macam mana hypothesis statement if the probability is not equal? Right. The probability is not equal. Hypothesis statement are same, right? Kalau kita tengok ni, let's say example number 3, right? The null hypothesis, it should be the proportion do not differ significantly, right? Because we don't have the same value of probability, right? Right. And the one in the alternative hypothesis, the proportion is differ significantly. So means the different differ very significant or not significantly lah. So kalau dekat sini kita tengok ni dia punya proportion ada difference sikit, tapi we don't really know whether the difference is significant or not significant, right? For this example, the modes of payment, the null hypothesis dekat sini, we want to know the objective is this is the hypothesis kita kat sini lah, significant level, whether the distribution of the modes of payment in express line change after the discount offer went to effect. So this is our alternative hypothesis. This is alternative hypothesis. Kalau this one dia kata apa? Differ are not, null hypothesis not change lah. So distribution modes of payment in express line not change after the discounts. So that one is null hypothesis. For alternative hypothesis, the distribution or the modes of payment in the express line change after discount offer when effective. Right? Right? So do you understand until now? So just a head start, before tomorrow I can start a new I can continue lagi tomorrow. Kalau you boleh join, make sure you join. I can continue on the next topic, which is others application, and we have a lot more coming, right? So for a start, I suggest you to solve example number 3 and example number 4 as your homework, right? Any questions so far? Ada soalan lagi? Before we end our session, do you have any question? Please write it on the chat room.
Sir, ada yang nak tanya soalan tu, sir.
So if the probability is not equal, dekat sini nampak tak? This probability is not equal kan? So nampak tak dia punya probability is not equal. So dekat sini our hypothesis dekat sini kan dia tulis sini. Now we want to know the proportion in the community differ significantly. Right? This is our null hypothesis. Based on the statement lah, kita akan tengok based on the statement. Right? So based on the statement, dia kata dekat sini, test 0.05% in level significant whether the proportion in the community differ significantly or not. So our null hypothesis is, our alternative hypothesis is this one lah. Our null hypothesis, the proportion does not differ significantly. Same goes to example number 4. So we want to find whether the distribution of the mode of payment in express line change after the discounts. Right? So this is our alternative hypothesis. Kalau null hypothesis, dia not change lah. Right? This is change for alternative hypothesis. For null hypothesis, not change. Okay, hope they answer the question. Soalan lain?
Sir, assessment 3 cover topik apa, sir?
Assessment 3 cover chapter number 3. Assessment 1 will cover example chapter number 1, 2 and 3. Right? So I ulang balik. Untuk our coming assessment on 20th June, we will have assessment number 3, right? Saturday kan, pagi pukul 9. On 27th June, right, we will have assessment number 1. We'll cover chapter number 1, 2 and 3. Assessment number 1 is our quiz lah. Assessment number 3 is test number 2. Right? Okay? Ada soalan?
Sir, untuk Sabtu ni berapa lama kita jawab soalan?
2 jam I think. 1 jam setengah, 2 jam macam tu.
Okay, thank you, sir.
9 sampai pukul 11. But it including your time to download and submit lah. Alright. Ada soalan lagi? If you don't have question, then we should end our session now. So make sure you treat the example number 3 and example number 4 as your homework, right? So make sure you understand the first part of chi-square analysis, and tomorrow we will try to do the second part of chi-square analysis, which is binomial and Poisson distribution. And hopefully you can copy the question, right? Alright, I think that's all. Thank you very much. Assalamualaikum.